This is section 1.3, acceleration. This is about change in motion. Any change in object speed, magnitude, direction, or both means change in velocity, means change in motion. This change in velocity is called accelerated motion. Acceleration describes how quickly an object velocity changes over time, or the rate of change of velocity. So for example, if you want to compare a car that is accelerating faster or slow, is how quick the car picks up the speed for a shortest period of time. That means that car is powerful, is fast, is accelerating quicker. Take a look on the diagram on the bottom right. It's a velocity time graph, and you see there are three graphs there. One is steeper than the other. So that means A is steeper than B and B is steeper than C. So the slope of that line represents average acceleration. That means that the object A is accelerating faster. That means it's picking up speed faster than vector B, than object B, and object B is accelerating faster than object C. So the formula of the average acceleration is AV is equal to delta V over delta T. So delta V is a change in velocity, and always change is about difference between V final minus V initial for interval of time. So average acceleration is going to be bigger if change in an initial and final velocity would be bigger, or interval of that change is going to be smaller. And this formula is one of the two most important formulas in kinematics. Here's some practice with the average acceleration. The velocity of the pack changes from 8 meters per second north to a 10 meters per second south over a time interval of 0.050 seconds. What is acceleration of the pack? So what is given? It's a V initial is 8 meters per second north, and V final is 10 meters per second south. Interval of time is 0.050, and average acceleration is required. So formula is average acceleration is equal to V final minus V initial over delta T. And we can plug numbers there. So V final is 10 meters per second south, V initial is 8 meters per second north, and interval of time is 0.050. We have a problem here because you have a south and north in the same equation. So we cannot do a mathematical calculation unless directions are the same. So that's why we flip one of them. It will make more sense to flip north to south because it has a negative in front. So when you flip the direction, the sign in front has to change as well. So that's what we do. Now we have 18 meters per second south over 0.0 over 0.50 second. That is equal to 360 meters per second square south. A race car is initially traveling at a constant speed when it begins to accelerate uniformly at a rate of 3.8 meters per second square backward. If after acceleration for 2.6 seconds, it now has a velocity of 137 kilometers per hour forward, what was the car initial velocity? So again, what is given and what is required? Average acceleration is 3.8 meters per second backward. So we can definitely use backward as a negative and forward as a positive, and we can convert it back at the end. This is for simplicity instead of using a big word on an equation. Interval of time is 2.6 seconds. Final velocity is 1.37 kilometers per hour forward, so that means plus 137 kilometers per hour, and initial velocity is required. So first we have to convert it to a standard unit because we're going to use those in an equation. V final is plus 137 kilometers per hour divided by 3.6 meter per second per kilometers per hour. That is 38.1 meter per second. Then we're ready to find initial velocity, which is V final minus A average delta T. Now we can plug numbers. Its initial velocity is 38.1 meter per second minus 3.8 meter per second square times 2.6. That is equal to 47.98 meter per second. So that's positive, so that means it's forward. If you want to convert it back to a kilometers per hour, now we have to multiply it by 3.6. But most of the time, you might not need to. If you remember, we studied acceleration using position time graph. So slope of the position time graph represents average velocity. Now we can study acceleration using velocity time graph. So they are similar with a time on a horizontal axis, but we have a velocity now on a vertical axis instead of position. The slope of the velocity time graph gives you average acceleration. So slope, which is a rise over run, is a change in velocity per interval of time. Here's an example. What is the acceleration of the skateboard in a motion between 0 to 10? So you have 2 points there. Interval of time is 0 to 10. Find the values of those 2 points. From a 0 second, the value of velocity is 0, and for 10 second, value is 30. So slope is a change in those values. So that's 30 minus 0 divided by 10 minus 0. Remember that. When you're going to do a slope, you have to write 4 points. Remember when you learn slope in a grade 9, it is y2 minus y1 over x2 minus x1. So has to be v final minus v initial over t final minus t initial. In this time, zeros do not make any difference, but you have to write it anyways because next time those 2 points might not be 0 and will make a difference. So average acceleration for this example is 3 meters per second square south. We can use velocity time graph to calculate displacement. For example, what is displacement of the skateboard in a motion between 0 to 10? The graph there is very simple graph. So we can calculate area under the line using the triangle area, which is base times height divided by 2. The base is 10 seconds, height is 30 meters per second. Then we can have 150 meters south. If you see the velocity label is south. For a complex, we can add areas under the graph for a known geometric figures. For example, you can split that into areas of the triangle and rectangle. You can calculate it as area 1 of the triangle, which is 25 meters per second, base times height divided by 2, and area of the rectangle, which is 5 times 10, 50. And then you can add those together and we have answer 75 meters south. If we have a table of values for a time and velocity, we can build a velocity time graph. So on a horizontal axis, we have time, and on a vertical axis, we have velocity. So here is table of data from 0 to 4 seconds and from 0 to 24. Again, when you draw a graph, make sure that you label the x-axis or a time axis to a 4 or closer to that number, but not less. Same thing for velocity. You can label it to up to 24, but not less. Here is how we draw it. So 0, 0, 1, 6, 2, 12, 3, 18, 4, 24. And if you have another one from 0 to 4, similar, but values of velocity are dropping. So then from 0 is 24, first second is 18, 2 second is 12, 3 second is 6, and 4 second is 0. So after you have those graphs, you easily can calculate the slope of that line that represent acceleration. So by looking at that line that goes upward, that means the slope of that line on a first graph would be positive, and the slope of the line on a second graph would be negative. So we can use slope as a rise over run or change in velocity per interval of time, which represent average acceleration. If you have noticed the speedometer in your car, it shows the speed at every moment. So instantaneous speed is a speed at a specific instant in time or at that moment. It is a scalar quantity as speed, and the symbol is just simple v. So you can calculate using a limits. So instantaneous speed is a limit where the time goes to 0, so very, very small interval of time, of delta d over delta t, which is a distance over time. The same way, you can calculate instantaneous velocity, which is a velocity at a specific instant in time or a moment. It is a vector quantity because a velocity is a vector quantity, and symbol is v with arrow on top. So we can calculate the value of the instantaneous velocity when delta t goes to 0. That means that for a very small interval of time of displacement over interval of time. And the same way we can calculate instantaneous acceleration, which is the acceleration at a particular instant or moment, which is a vector quantity as acceleration, and symbol is a with arrow on the top. So this means that we evaluate the average speed or velocity or acceleration over a shorter and shorter period of time. As the time becomes infinitely small, we have instantaneous speed or instantaneous velocity or instantaneous acceleration. We can use a graph to calculate instantaneous velocity if there's a position time graph, or if there's a velocity time graph, we can calculate instantaneous acceleration if at any point, if we draw a tangent at that line. So the instantaneous velocity or acceleration is a slope of that tangent line. So that's how you draw a line. That line touches the graph at one point only. As average has to join 2 points in a graph, average between 2 points, the average in the interval of time of those 2 points. As you move closer to the interval of time, then that average becomes a tangent on a certain point. So make sure the tangent does not cut the graph. It touches the graph in 1 point only. By looking at the position time graph, you can determine what time of motion you are talking about, what type of velocity you're talking about. If the line is a straight line in a position time graph, so the slope is going to be a constant. That constant, that slope represents velocity. So what we are talking about, it is a motion with a constant velocity or a uniform motion. If in a position time graph, if the tangent changes, so that means if the instantaneous velocity changes, that means it is an accelerated motion. So change in velocity means there is acceleration. That means it's an accelerated motion. We know that instantaneous velocity is the slope of the tangent line to that curve. And you see a position time graph given. It's a parabola. There is not a constant motion, it's an accelerated motion. If you see that tangent will on the different points there will be different. So let's start with 3 points, 0, 3, and 7. 0, you don't really need to draw anything because that is going to be a horizontal line. And you know the slope of the horizontal line is 0. So let's start with the number 3. So you can draw a line there that is going to touch that curve in one point only at 0.3 second. Then you can get that point and you look for another good point. What would be a good point? Good point would be, for example, 9. That you clearly see the value of 9s correspond with a value of 125 meter west. So then you can get 2 points. That will be a final minus initial, or y2 minus y1, or d final minus d initial divided by t final minus t initial. So 125 minus 25 divided by 9 minus 3. So the value will be 16.7, which is positive, and it's meter per second west. So let's draw a tangent at 0.7 second. So with a ruler, you draw a line that touches the curve at 1 point only. Then you look for a good point, which you can easily read the value from a graph, which is 4. You can clearly see that 4 correspond with a value of 25. Then you can do a rise over run, 150 minus 25 over 7 minus 4. Another example that you need 4 values of those 2 points. So 2 values of vertical and 2 values of horizontal. Never just 2. You need 4. 2 up, 2 down. And that will be a correct one. So slope of that tangent line at a number 7 second is 41.7 meter per second. So after getting those values, 0 and 0, because the tangent of the 0 is a horizontal line and slope of the horizontal line is 0, time 3, and we have the slope 16.7, and times 7, you have a slope of 41.7. So with 3 points here, we draw underneath that position time graph, we draw velocity time graph. You have to be careful because time has to match. Time of a velocity time graph and position time graph has to be exactly the same because we are talking about the same motion that flows at the same time. So what we can do, you can plot those pairs of values, 0 at the time 3 and at time 7, and then you can draw what we call line of best fit. Then we can calculate the slope of the line of best fit, which in this case is 5.63 meter per second square west. So why west? Because it takes the direction of velocity, and that is positive slope, which is the same direction. And this is how you can derive a velocity time graph from position time graph. So let's summarize this. You can pick 3 or 4 points there. You can draw a tangent on those points, calculate a slope, get those values, build a velocity time graph with a time that is exactly the same as a position time graph. Then you plot those numbers, draw a line with the best fit, line of the best fit, and you calculate a slope of that line using exactly the same thing that we did before, using a rise over run, and that is acceleration. And then you can build acceleration time graph. We're going to do that later on from velocity time graph, which is going to be a horizontal line of 5.63, which is going to be a positive value. So that's how you do it. Here is a practice of solving problems. A train moving in a straight line with an initial velocity of 0.5 meter per second, accelerate at 2 meter per second square for 2 seconds. It continues from 0 acceleration for 3 seconds, and then accelerate with negative acceleration, slows down with 1.5 meter per second square for 1 second. So what we are looking here are those segments. From 0 to 2 is accelerating with a 0.5 meter per second, then is not accelerating at all for 2 to 5 for 3 seconds, and then is slowing down for 1 second, 5 to 6. So what is looking here is final velocity of train after 6 seconds. So there are 3 changes, and we can calculate final velocity separately for each segment, or we can just calculate as a change in velocity. So what do we have as a given? We have initial velocity of 0.5 meter per second, then acceleration 2 meter per second square for 2 seconds, and then 0 for another 3 seconds, and then minus 1.5 for 1 second. What is final velocity? The formula is initial plus change in velocity. So change in the velocity is a delta t. But that changed 3 times, 3 segments, different segments with a 3 different interval of time. So we can do the same thing by now replacing those symbols with the numbers that we have, the given values. So the initial is 0.5 meter per second, then A1, acceleration on segment 1 is 2 meter per second square for 2 seconds, delta T1, plus 0 meter per second, which is A2, times 3 second, plus minus 1.5 meter per second for 1 second. And then you get 3 meter per second. Now, if you take a look on the graph itself, it is very clear that that final is exactly 3 meter per second. However, I'm going to warn you something. You have a graph and you have the problem, word problem with values. You're not going to have that often, graph and values. The graph here is just to give you an idea that how that motion is. How can you understand better? But obviously has to be one or the other most of the time. So B is asking for average acceleration of the train. So let's get those 2 points that you can calculate the final and initial velocity for final and initial time. So initial velocity is 0.5 for initial time 0, and final velocity is 3 meters per second for time, which is 6 seconds. And then you can calculate average acceleration as a v final minus v initial over t final minus t initial, which actually is a slope of that line. Then you can plug those numbers and you get the average acceleration is 0.42 meters per second. Now, in this diagram might look a little bit complex, but is the connection between a direction of the acceleration and a direction of the initial velocity. So how do you know what is going to happen? How is connected? So if you take a look, there is a initial velocity here is bigger than final. So it's going to get smaller. So if the final velocity gets smaller, that means that it's slowing down. So what does it mean? When it slows down, then the acceleration has to goes against initial velocity. So if initial velocity is positive and slowing down, then acceleration has to be negative. Now, if this car turns curve, then acceleration that we're going to learn in grade 12 is directed toward center of that circle, of that curve. That car is going through that circular motion. More about this in grade 12, chapter 3. But for now, what about when it speeds up? So that means that acceleration has to be at the same direction as initial velocity. So it is helping initial velocity to become bigger, faster. So it is like when you push the gas, that acceleration is in same direction as initial velocity, it's going to speed up. When you push brakes, then acceleration is in the opposite direction of the motion. That means that velocity will slow down. Here you see animation that when acceleration and velocity are the same direction, the object will move faster. When acceleration and initial velocity are at the opposite direction, the object will slow down. And on the curve, acceleration is always directed toward that center of that curve, and then it's slowing down because it's in opposite direction of that motion. So again, you know when acceleration will increase or speed up or decrease an object. So here is an example. At the diagram A, you see that acceleration and velocity are the same direction. At the diagram D, acceleration and velocity are at the same direction. So the expected value here would be accelerating. Final velocity is going to be bigger than initial velocity. Now take a look of diagrams B and C. So either in a positive or negative doesn't really matter. What matters is the opposite of each other. So if acceleration is negative and velocity is positive, that will make the car to slow down, or other way around. If the velocity is negative and acceleration is positive, it's going to slow down anyways. So when we calculated acceleration, we found that acceleration formula is A average is equal V final minus V initial over delta t, and then you can actually solve for V final, which is a V initial plus A average times delta t, or V initial, which is V final minus A average delta t, or from an interval of time is a V final minus V initial over A average. So the velocity changes linearly at a straight line. So then in that kind of motion, we do use those formulas. We cannot use formulas if the acceleration is changing over time, which we can use graph, but we cannot use those formulas. So what we are looking for is motion with a constant acceleration, or what we are calling uniformly accelerated motion. Most common position time graph for a uniformly accelerated motion or motion with a constant acceleration is parabola. That is very known graph, which you can derive velocity time graph and acceleration time graph from this type of curve from parabola. Interpreting position time graph. State the direction of the velocity and acceleration in terms of positive or negative. So let's start with the graph A. If you look at the graph A, and if we need to draw a tangent here, that is going to go down, right? So that means that velocity is negative. However, if you see that velocity become steeper as we go in the time, so that means velocity becomes bigger. So since that velocity is negative and becomes bigger, acceleration has to be at the same direction. So acceleration has to be negative as well. For graph B, it is very easy because it's a straight line going up is a positive and acceleration is 0 because it's a uniform motion. Is a slope of that line is a constant, so acceleration is 0. Okay, so next one would be graph C. The graph C, if you draw a tangent on a graph C, it is going up. But as it goes from this point here, for example, to draw a tangent at this point, that is going to be less steep. So that means it's slowing down. So since that velocity is positive and is slowing down, the acceleration has to be in opposite direction of positive, which is negative. D. D is the opposite of C because actually velocity is up, but is becoming steeper and steeper, faster and faster. So that means that acceleration has to be at the same direction as velocity. So both has to be positive. And E, position does not change. That means velocity is 0. And if the velocity is 0, acceleration is 0. You do the same thing with the graphs that are, if you see that the graph at graph A is getting steeper and steeper, so that means that object is accelerating. So other one is negative, but is still getting steeper and steeper. That means that both objects at the graph A and the graph B are speeding up. On this pair of graphs, so you see the tangent is positive, but is getting less steep. That means is slowing down. So velocity is positive, acceleration has to be negative in order for the final velocity to be smaller than initial velocity. So is slowing down, positive velocity, negative acceleration. And other one actually is negative velocity because it's going down, but it's getting less steep, still negative, but less. So that means since the velocity is positive, has to be in the opposite direction, which is negative. So that's about it. This is how you can interpret the graphs on position time graph for velocity and acceleration. By looking at it, you can determine what kind of motion is happening in this graph. And that is section 1.3. Thank you.